welcome to the basic presentation on seismic survey. You have done this module before, but it is good to recap once again towards the end of the syllabus so that we understand the core of this subject. The core of the subject was seismic survey, seismic processing, and seismic interpretation. We will be giving you once again a glimpse of what we have revised in the class so that it is understood clearly and can be applied for the interpretation purpose. Now, seismic methods are by far the most important geophysical technique. The predominance of seismic method over other methods is due to various factors. Important to note are high accuracy, high resolution, great penetration of which the method is capable. Seismic reflection survey widely used worldwide for hydrocarbon prospecting. Now we know that there are three types of survey, the 2D survey and the 3D survey. An advanced method is the 4D survey. 4D survey is a multi-component survey which is done as a time-lapse survey. It is a 3D survey which is repeated after the production wells are drilled and production happens, so that we can understand how that hydrocarbon has moved when the production took place. Seismic methods can be dealt in three different phases: acquisition, processing, and interpretation. Now the basics of seismic is what is important is grabbing echoes. Models a view of the earth in terms of velocity and density. Now then, based on this model, we drill wellbore geometries and wells are utilized for exploiting the hydrocarbon. Now, view of a geologist in terms of the lithology. So, when the ray is ignited from the source and it goes into the receiver, a geologist tries to look into the two-way time in terms of lithology, whereas a seismologist or a seismic interpreter looks it in terms of velocity and density. The product of velocity and density is known as acoustic impedance, and which see the change of acoustic impedance across the boundary. So we can find out the reflectivity. The reflectivity is calculated as ρ2 V2 minus ρ1 V1 divided by ρ2 V2 plus ρ1 V1. Based on whether the reflectivity is positive or reflectivity is negative, we can have either peak or trough, and the wave shape gives an important clue which we have seen in the attributes in understanding the hydrocarbon presence. Now, in order to do the seismic acquisition, the seismic waves understanding is important. Seismic waves are waves that propagate through Earth's interior. The propagation velocities of seismic wave are determined by elastic module and densities of material. There are two types of seismic wave: body waves and surface wave. Body waves, these waves travel through the interior of the Earth and they arrive before the surface wave emitted by an earthquake or by man-made disturbance. These waves have higher frequency than the surface wave. There are two important types of body waves which you need to remember always. One is the P waves, which is the primary waves. P wave is the fastest seismic wave. They can travel through the solid rock and liquid as well as air. It causes particles to move in directions as the wave energy is traveling. S waves are slower than P waves. S wave only moves through the solid rock. Highest velocity in crust is 3.6 km per second. Particle motion is perpendicular to the direction of propagation, so it's transverse. Now here you can see once again through a diagram that primary waves, the wave motion is in parallel to the particle motion, which is not true in case of shear waves or S waves. In this case, the wave motion is perpendicular to the particle motion. So these difference should be kept in mind, that how the wave is propagating in the subsurface in terms of P and S wave. P wave can be converted into mode converted S wave, which is also important to understand because in the subsurface there are always mode conversion happening. Velocity of P waves is given as square root of k plus 4 by 3 mu by rho, where k is the bulk modulus, mu is the rigidity modulus, and rho is the density. whereas the S wave is given as square root of mu by rho, where mu and rho are rigidity modulus and density respectively. The K term is missing here. We should also understand the surface waves, because surface waves are considered as noise. This has to be removed during the process of refraction. So we should also understand that what is the depth to the low velocity layers, because surface waves are low velocity layers, and we have to remove the low velocity layers to bring the datum from the surface to the bottom part of the low velocity layer, which is useful for seismic reflection. So surface waves only travel through the crust. Surface waves are lower frequency than the body waves. There are two types of surface waves which are important to understand. One is called love wave and other is called Rayleigh wave. Love waves are faster than Rayleigh waves. Particle motion consists of alternating transverse motions, whereas Rayleigh waves are retrograde elliptical in motion. A Rayleigh wave rolls along the ground just like a wave rolls across a lake or an ocean. Particle motion, as I told, consists of the elliptical motions in vertical plane and parallel to the direction of propagation. We should know the surface wave very minutely, because this has to be studied, this has to be removed, and all the clay bands which are there in the low velocity layers need to be understood from the refraction, and the depth to the low velocity zone also need to be understood from the refraction survey. So refraction seismic precedes a reflection seismic, and both should be done in order to have a good data content, because signal to noise ratio is very important in case of seismic in order to understand the content of energy there, the content of amplitude, because all these are used for structural interpretation and also stratigraphic interpretation. Here is a diagram of the love wave and Rayleigh wave. We'll go into the detail and revise what is acquisition is about. The acquisition consists of a geophone, which is the detector. Then we should have the source, which actually sends signal into the surface, and we should actually have a recorder where recording takes place in a chart called seismograph, which shows the amplitude versus time. We see the peaks in the wiggle trace, we see the zero crossing trough, and then once again peaks. Amplitude is pressure, displacement, particle velocity, and acceleration. What is the workflow of acquisition? Now I'll go step by step on the workflow. Two radio frequencies are used in seismic surveys on the connecting between the shooter and the observer on the receiver line, and the seismologist sits in the instrument van where we have the instrument to record the data. The other frequency is used for logistic purpose. A refraction survey is preceded before a reflection survey, which I told you before, in order to understand the thickness of the low velocity zone. For a reflection survey, the short hole depth should be below the low velocity zone. This should be kept in mind. In reflection survey, when we fill the short hole with dynamite, that filling and blasting should be taken place in the same day, because we cannot fill these short holes day before and then blast it next day. A test survey is mandatory for 1 or 2 days to perform an optimization for short depth, charge size, which can be between 1 kg and 5 kg of dynamite, and the group interval and short interval to be deployed for the survey. Once the short hole is drilled, the dynamite is placed into the short hole, and the short hole is filled with cow dung and tampered well so that good coupling exists between the charge and the borehole. Once the dynamite is ignited, the vibration from the dynamite sends impulse inside the earth, which get reflected, refracted, and diffracted from the various layers inside the earth. The geophones are meant for measuring the refraction, so they are called refraction geophone. For getting the data for the reflection, we utilize reflection geophones. So the geophones are different for reflection or refraction. That should be kept in mind. The reflection geophone planted in the receiver line will receive only the reflection P wave component. This signal is sent to the recorder, and a chart is prepared under the supervision of the seismologist, which is called a seismograph. Now here are the example of seismic refraction and geometry and seismic reflection geometry. We can see the short point, and after that the geophones are placed. One of the important understanding is how the geophone distance should be. So that is called the group interval. The separation between two shots, that is the first shot and the second shot, is known as short interval. So short interval and geophone interval are important components to understand the subsurface fold. The subsurface fold is defined as the number of times the subsurface point is illuminated. So if a subsurface point is illuminated 3 times by a different source receiver pair, then the fold of the data is 3-fold. As we improve the fold of the data, the signal to noise ratio improves. The signal to noise ratio is proportional to the square root of the fold. The distance between the shot and the first geophone is known as near offset, and the distance between the shot and the farthest geophone is known as far offset. So in this case we can see the bedrock and the overburden, and we can see the refraction happening and the reflections which are taking place. Now in case of refraction, we have already told that it is needed to understand the depth to the low velocity zone. The time distance curve prepared from the refraction is important to understand the first break. So the direct wave and the first breaks, the refractions which are utilized in order to understand how many layers are there in the low velocity zone. Now in case of a 2-layer case, we have the T is equal to x by V2 plus 2h cos theta by V1, where x is the offset, V2 is the velocity of the second layer which goes to infinity, and V1 is the velocity of the first layer, theta is the depth of the bed, and h is the thickness to the low velocity layer. So that's how it is utilized in case of refraction. In case of reflection, we normally utilize the geophone in placing on one side of the shot. This is known as end-on shooting. Now in the end-on shooting, we have all the geophones placed on one side of the shot, but in the diagram shown here, geophones are placed on both the sides of the shot. Now these are very important to understand in case of dipping bed. So we can have symmetrical shooting or asymmetrical split spread shooting. So there is a split spread here. The spread on one side of the shot can have more geophone than the other side, which is known as asymmetrical split spread. If the number of geophones on both sides of the shot is same, then it's called a symmetrical split spread. Now in order to understand the time-depth relationship in case of a reflection, we know that t square is equal to t0 square plus x square by v square is the normal move out which takes place from the shot to the geophone. Now if there is a dip of the bed, then t square is equal to t0 square plus x square by v square cos square theta. X is the offset and t0 is the initial time. Now x square by v square cos square theta can also be broken as x square by v square minus x square by v square sin square theta. Now t0 square plus x square by v square is known as normal move out, whereas x square by v square sin square theta is known as dip move out. Symmetrical and asymmetrical split spread are decided on the dip of the bed and direction of the dip. I have already given you an exercise to draw how the ray path will look like in case of a dipping bed, and whether you will be choosing more geophones on the down dip and less geophone in the up dip, or the reverse scenario. Now here is an example of a field layout. You can see the reds are the shot lines and the browns are the receiver lines. The truck you can see there where the data is getting grabbed or captured, and we have the geophones and the shot point. It can be in the 2D or in the 3D. The difference between 2D and 3D is that 3D has an X, Y and a Z component which is the azimuth, whereas in the 2D we have X and Y. A closed grid 2D can give result into a pseudo 3D concept. Now also we should understand what are the sources which are used in seismic. These are seismic acquisition, which is used with the help of dynamite. On the top we have seismic acquisition on land using vibrosis, and at the bottom we have a seismic survey vessel. I have given you an exercise to decide on what are the types of sources you will be employing for acquisition of seismic. Now, geophone is one of the important instruments in the acquisition of refraction and reflection geophones. Geophones are detectors consist of a coil of wire and magnet, one of the two elements being fixed as rigidly as possible to the Earth's surface so that it will move along with the Earth in response to the seismic disturbances. The other element is inertial and is suspended by a spring from a support attached to the portion that moves with the Earth. Relative motion between the two produces an electromagnetic force between the coil and the magnet, the voltage being proportional to the velocity of the motion. The electromagnetic geophones with moving coils are standard detecting units for work on land. Now for geophone we have the natural frequency between 10 to 70. Refraction survey sometimes below 10 frequency ranges are also used. 70 to 140 is used for reflection survey, used specially in land. In the Mars we have the Mars phone, which has a natural frequency between 10 to 14 Hz. We use this in transition zone. Hydrophones have frequency range between 10 to 14 used in the marine, and 3C receivers have frequencies between 2 to 8 Hz normally used in shear wave acquisition. There are pressure phones or hydrophones which are used for marine survey. We don't use geophone in the marine survey. Pressure phones are commonly used for receiving signals in appreciable depth of water. Special waterproof cases have been designed to permit planting of moving coil phone in ground. Pressure sensitive phones, often referred to as hydrophone, uses piezoelectric crystals as pressure sensors. They generate a voltage proportional to the instantaneous water pressure associated with seismic signal. It can be shown that this pressure is proportional to the velocity of the water particles set into motion by the signal. Now the seismic recorder is the third thing which need to be understood, because the fold is calculated as half into number of geophones group interval by short interval, and as I told you that the more the number of channels are there, better is the fold. However, there is an optimization in the fold. After some time the fold reaches the optimized value and it becomes plateau. If you improve the fold, the subsurface illumination will not improve. Today, majority of the acquisition system provide 24-bit recording technology. A 24-bit technology system offers high fidelity because it records data over large dynamic range. True telemetry systems have no physical connection between the station recording unit and the control system in the recording truck. This system should be used where access is limited due to rugged topography, permit problems, or any other reason. Search-Cell Eagle system is an example of such system. The SAR, the Seismic Acquisition Remote Unit, records the signal and sends it via radio frequency to the control recording station. Here is an example, real field example from the field party camp. You can see that this photograph was taken in Tripura in 2005. You can see the bunkers which are there where the recording stations are there. In the evening, we try to see how the shots which we have blasted and how the records which has happened in the morning looks like. If we feel that the record is not good, we reject it and we plan next day to reshoot it. We also plan in the night that how the shooting pattern will be for the next day. It is important to understand on the software that the record which has been recorded, did it give the good signal to noise ratio, is the target length good, and whether the horizons of interest which we would like to map is well recorded or not, and a decision is taken whether to accept it or reject it, and then re-record it next day. This is a seismic data acquisition. We know that the subsurface, they are layered. We can see layer 1, layer 2 and layer 3. The shots are there which are equispaced, and receivers are also equispaced. The first shot got blasted and the energy got reflected from layer 1, layer 2 and layer 3, and it goes and received in the receiver. So that's how we acquire the data in case of 2D. There are certain parameters which are calculated and should be kept in mind while we acquire the data. One of them is the target layer. The target layer is the horizon of primary interest for the survey. When parameter conflicts arise during design, the requirement for the target layer should prevail. For imaging the target horizon, geologic knowledge of the expected thickness and reflectivity is needed to be estimated. We know that by Rayleigh's criteria, the thinnest bed which can be calculated depends on the tuning thickness. This is known as the Rayleigh's criteria, and it is calculated by lambda by 4 because lambda is the incident wavelength, and we know that Rayleigh's criteria is given as lambda by 12, but for all practical purposes the tuning thickness is calculated as lambda by 4. The group interval is a basic sampling on the earth by the survey. It is the distance on the ground between receiver stations. Group interval represent which largest spatial sampling shall prevent aliasing during migration. GM is given as 0.5 Vm by, that is the B minimum by F max sin theta. B minimum is the minimum velocity in the beds. Theta is the maximum dip of the target horizon in degree, and F max is the minimum frequency, or rather the maximum frequency expected. Record length. Part of the survey design is to determine the required sampling rate in time, and record length is a function of depth and velocity of the deepest horizon. Sample rate. The sampling rate is time in more or less standard, ranging from 1 to 4 milliseconds. Fold coverage is an important aspect in the acquisition of the data. For flat layers or the dipping layers, the fold is calculated as half into number of geophones into group interval by short interval. The foldage is equal to signal by noise whole square. We also should know what is the vertical resolution of the data, which is given by the Fresnel zone. The maximum group interval is given as 4r by 3, where r is the radius of the Fresnel zone. Far offset is the function of the depth modified by the velocity field, and also we should know that how to calculate the far offset, which is given in this calculation. Here is an understanding on the refraction seismic method. These are employed, as I told you, mostly to understand the low velocity layer. There can be couple of layering within the low velocity layer. We have to understand how many clay bands remain in the low velocity layer, and that helps us in understanding the subsurface picture better. That helps us to drill short holes which should be below the low velocity layer for the reflection survey. In the reflection survey, there is an introduction of seismic pulse into the ground, pulse spreading outwards as a downgoing seismic wavefront. Reflection happens at the boundary between the dissimilar rock layers. The pulse travels upward as a reflection wavefront. Recording happens at the receiver near the earth surface. When we acquire the data is in time sequential format. The gathers of different types should be analyzed in order to understand whether we are getting good reflectivity. In this example, we are getting good reflectivity, but they are cut by diffraction. The diffractions are noise which need to be removed, and as we will talk about the processing, we will see how the diffraction noise can be removed from the data. Here is an example of a common shot gathers where the shot has been blasted, it hits the reflection surface and goes to the receiver. we can see that there are 3 receivers. Each point here is covered only one time, so the fold of the data at this moment is one fold. Gathers of different type. This is an example of a common receiver gather and common midpoint gather, where we can see that there are 3 shots. It goes to the receiver, whereas in the common midpoint gather we have shots, 3 shots and 3 receiver. The subsurface point is illuminated 3 times. This is an example of a 2D seismic complex reflections which are happening in the subsurface. From this we calculate the two-way time, and from that two-way time we try to see how the reflection acoustic boundary looks like. We need to process the data, and first part of the processing of the data is converting the sec-d data into sec-y format. As I told you, the data is acquired in a time sequential format which need to be converted into trace sequential format as we go into the processing step. And this is an example of a 3D seismic where the grids or the bin size has been talked about. In my presentation on 3D seismic, I have defined what is bin. I have also defined how the shots per square kilometer need to be calculated, how the source line spacing should be, and how the receiver line spacing should be. The azimuth is a very important criteria in case of 3D seismic. Here is a display of the 3D seismic where we can understand the acoustic impedance contrast. We have made a chair cut display here. We are seeing that the acoustic impedance are very well mapped, very well acquired, which can be mapped very well, and that is what is the motto of the seismic acquisition will be. The 4D seismic is a time-lapse 3D seismic to detect the changes in the seismic response of a reservoir over a period of time, thereby understanding the behavior of the reservoir fluids. With this we come to the end of acquisition. The next presentation will be on the processing. We will see the processing steps which are involved in order to understand how much data processing is required to have a meaningful data, to have a very good signal to noise ratio in order to give a meaningful interpretation to the data. Thank you very much.